So, this lecture deals with concentrating collectors. Before we go ahead with the concentrating collectors, one or two topics that were left out in the previous lecture in connection with flat plate collectors, or in fact, some of them are common to concentrating collectors also. We will deal with it. First, we discuss the optimum slope for flat plate collectors. The best way is to calculate the total radiation received by the collector in the year, even based upon the monthly averages, and depending upon your objective, you maximize the total radiation received over the year or whatever is the application that demands. Now, the other thing, when we talk about a single collector in a classroom type of situation, it may be going here to a tank, and it may be recirculated through a pump through this. We can say here is sort of a heat exchange. Very simplified system diagram. This is the collector. Still, if I want, I may have a control which ensures that the exit temperature is higher than the inlet temperature. From here, I may take it to the load. So, if there is no heat exchanger, I can assume effectiveness to be unity, that will come to about it simulation later. So, it is very nice to talk about one collector, and then also people say why not we use the optimum angle every month, change it once a month. So, it might not be a very bad idea, but now imagine a solar water heating system. Something like, let us say, 80,000 liters per day. I am not exaggerating. I have known larger systems than this, which I will mention a little later, supplying energy at about 70 degrees centigrade. So, this will require approximately, if I may say so, 80,000 divided by 50, that comes to 1600 meter square. At 70 degrees centigrade, I am assuming 1 square meter collector area will deliver about 50 liters per day. So, this comes to about 1600 meter square. So, if you take 2 square meters as the area of the collector, there will be 800 collectors, all of them connected to each other. So, it is not a easy thing to change the slope every day and every month. Consequently, depending upon the application, we find the optimization. That is what we were trying to say in the earlier topic that we considered. Now, the solar collector arrangements. How do I connect these 800 collectors, or just let us talk about a less number for the convenience of drawing, maybe 12, 13, 9 or 16 collectors. One way is, I will take it for the time being, just 6 collectors. So, let us say there is a large header connected to this, connected to this, connected to this, and all the 6. Then again the delivered hot water will come out through these 6 collectors, and I have some sort of a pressure balancing, so that the flow through each collector is uniform in addition to the headers and risers that we discussed providing uniform flow in the collector. This is one arrangement. So, T I is same for all 6 collectors, and similarly T O also is same for all 6. We are assuming that there is a uniform flow rate and all the collectors are same efficiency. Consequently, nevertheless, it will enter at T I and come out with T O. So, the flow rate, if this is m dot total, we have got m dot upon 6 through each collector. Okay. So, the corresponding the pressure drop will be that due to m dot by 6. Instead, I will have the arrangement like this. They have become little smaller because I have to adjust it in the height of the paper in the landscape mode. Okay. Oh, one more. That is it. So, this centers at T I. In general, this may go out at T O dashed, which may be different from T O when they were all in parallel. This is collector number 1, 2, 3 and 6 m dot. So, m dot flows through all collectors. So, this has got the advantage of a uniform flow rate, perhaps better maintained through all the collectors, but 6 times the flow rate will be going through each collector. So, I can expect delta P higher in this arrangement for this arrangement compared to a parallel. Whatever we have discussed earlier. So, we can see that this is one extreme and this is another extreme. This has got the little bit of disadvantage of poorer heat transfer and less higher chance of non-uniform flow rate. The last collector, imagine 800 collectors, we may not get the same flow as the first one, whereas here the pressure drop is higher. One more thing which is often ignored or not really taken into account, when you have got series collectors, again we will discuss in little bit in detail when we consider the critical radiation level. Let us say this is T I and this adds a delta T 1 and this adds a delta T 2, obviously less than delta T 1, since this is at a higher temperature and hence higher losses. So, technically the efficiency of each subsequent collector will be lower than the previous one. Now, it may so happen that this T I 3, this will be T I 2, this I may call it T I 1. So, T I 3 is much higher, consequently the so called critical level radiation may be higher than the solar radiation falling on the collector. In other words, a stage will come where the last of the collectors may not be able to provide further heating to the fluid that they receive. So, this is one danger one has to reckon with when the collectors are in series compared to in parallel mode. So, one can think of a combination of these things. Series we have considered, parallel we have considered, and series parallel. So, 3 collectors over here, they are in series and they are in parallel with another 3 collectors. That means, my original 6 collectors have been connected like this. So, that if this is my m dot, this will have m dot by 2, this will be having m dot by 2 compared to m dot had they been completely in series. You know that the pressure drop is highly nonlinear with the flow rate. So, there will be a significant reduction if you make it a series parallel. The other way around could be parallel series, though technically they are distinguished, but the idea is the same. These are in parallel then I have. So, this is so, it is a question of I have deliberately chosen 6, so that I can make 3 of them in parallel with 2 series and 3 of them in series with 2 parallel, call it parallel series or series parallel. Now, it is very difficult to say which one will have a higher pressure drop, but you can see that the total flow rate is m dot, but through each will be m dot by 3 and here also m dot upon 3 compared to m dot upon 2 in the previous case through 3 collectors. So, I can expect this to be having a lower pressure drop, though one has to worry about the additional piping that this may require. So, these are the issues when you talk about not a single collector like in the classroom. We have a large system supplying thousands of liters of water, which may have 2000, 3000 square meters of area of collector with about 1000 to 2000 collectors of each 1.5 to 2 square meters of area. For n number of reasons, one has to connect them in parallel or in series or series parallel combination. If they are all in series, first of all the land area geography or topography has to be something. Of course, it is not that I cannot put it side by side and still make it series, but then the one has to worry about the losses through the pipes also. So, apart from the land restrictions, one has to really work out through a simulation or a calculation procedure what gives you the optimum heat transfer enhancement or advantage vis-a-vis the additional pumping requirement. Then I will just touch upon a solar simulator. This is for testing of solar collectors. Of course, one can go ahead and do the outdoor testing, but no matter how careful one can be, the conditions cannot be identical when the tests were conducted on different days. So, if you want to compare two designs, then outdoor testing, if the difference in the efficiency is 10%, 8%, one can take cognizance of, but then if it is 1 or 2%, the uncertainties owing to the different climate conditions may be larger than the difference in the efficiency that it is shown. Consequently, it may be a little tough to take a decision about which collector is superior in case apart from the cost consideration. One is 37% tested in February and the other is 39% tested in summer. I really have no idea which one is really superior. So, it is very difficult to assess that type of a small difference. 30 to 40, yes, okay, the difference may not be 10%, but the higher one is likely to be higher. So, for comparative purposes, number one, you can say for comparison and for indirectly research and development, after all, you propose 2 or 3 designs, you test it under identical conditions and come out with this, okay, this design is better than the other. Then invariably solar simulators are used. In addition, the advantage is that not only you can have a controlled solar radiation, it can be done indoor and it can be done all the 365 days of the year without worrying about rain, high wind or any cloudy condition, etc. If you consider or account for all these things, you may not have more than 200 days of clear days, less than that in fact, to test a solar collector under the recommended testing conditions. So, solar simulator could be a alternative, but the compromise is spectrum. Will the solar simulator give the solar spectrum? That is question number 1. Secondly, uniform intensity. After all, though the sun is at a large distance from the earth, the size also is pretty large and the intensity of the solar radiation on collector can be expected and is uniform. Whereas, if you have a solar simulator, depending upon the distance from which you keep the solar collector and the simulator, you may have a difference in the intensity on the collector surface. So, usually halogen lamps produce a spectrum close to solar radiation. So, one can think of a bay of halogen lamps, Philips makes them in India. Maybe you may have about 12 or 14 as the case may be, and you arrange them at distance best decided by trial and error. Each one is about maybe a 1 kilowatt. So, a simple arrangement can be made that the angle can be changed. If this is the one, you may keep your collector parallel to this with your, of course, flow and other instrumentation. This is your simulator, and you use a pyranometer on the collector surface and ensure whether the intensity is uniform or not, and if it is within plus minus 5% or so, it is okay, and you can bring down, if necessary, move it nearer. If you want a higher intensity, move it away, that is one way, or change the voltage. Voltage applied through a variac can be up or can be down, of course, within 220 volts supply limitations, and then you can go down to 100. Then once again the problem is that of the spectrum. If the voltage is lower, it may not produce the same spectrum as that at the full thing. But simulator results can be depended upon to the extent of establishing relative performance of different collectors. So, we go on to the next topic of concentrating collectors. So, we explored improving the efficiency or the operating temperature for the flat plate collectors through one or two or more glass covers, better insulation and even evacuation, though it may or not be practicable or to have a completely evacuated flat plate collector. So, the next idea is to have what we call concentration, and the very early type of concentration you can see it in the form of mirror boosters. So, if you have, I will first give you the configuration, so that you will understand the whole idea. Suppose I have a parabola, this is a reflecting surface, and this is the focal point. So, all the rays falling on the reflector will be reflected onto this. Now, to fix the idea, let this be AA, I will give you the name, let this projected area be AR. AA is the aperture area, and AR the receiver area. Okay. So, whatever radiation is received by this aperture is reflected onto AR. So, now if I write the energy balance, QU should be equal to IT times some optical efficiency, I will call it for the time being, times AA. So, my solar radiation IT is based upon the unit area of the collector or the aperture area, sorry, minus the losses that will be taking place from the receiver at temperature TR and the ambient temperature TA multiplied by AR. So, now the collection is through AA and the losses are through AR, which AA is let us say much greater than AR. So, now if we try to write it per unit area or like in the standard form, I can write it as AA times IT eta optical minus UL times TR minus TA times AR upon AA. Now, if I define CR a geometric concentration ratio AA by AR. So, QU can be put in this particular form AA times IT eta optical minus UL by CR times TR minus TA. Now, this clearly shows if CR is high, of course, it is greater than unity in order that there is concentration and not diffusion. If CR is high, I can have for a given TR can be high. If you compare with a flat plate collector, if I choose this concentration ratio as something like 10, I may have a delta T 10 times larger for a given UL at the corresponding critical level. So, this is essentially increasing the effective intensity of solar radiation on a receiver area AR collected from an aperture area AA. So, this receives what you need is focusing. So, the solar radiation that is coming onto this parabolic reflector should be always parallel to its axis, otherwise it will not be concentrated at the receiver where it is kept at the focal point. So, this also can be done with a reflector as we have discussed or with a refractor. Many of us might have had experience in trying to burn a paper with a convex lens and sun's rays, childhood, and then paper and it gets burnt, because all these rays are concentrated at a finitely small area. So, here are certain pictures that will show you different concentration methods. The first one is almost like the mirror booster which we have discussed. Okay? Basically, these two are the boosting surfaces which will come over here. This will directly receive and this will be reflected, this will be reflected onto this. And of course, which we have discussed this parabolic, or it could be even a paraboloidal. If you see the dish antenna, it will be of the same shape, and here is the focal point and the sun's rays coming onto this will be reflected onto the receiver. So, when the size is a limitation, people have, you can see a heliostats, smaller mirrors or lenses focusing onto a central receiver. so that breakage of one does not bother the remaining ones. So, you can have a Fresnel lens that is essentially something like this at okay, micro grooves, this may be up, and then how does it go? Okay. Okay. So, whatever is through the similarly, you can arrange even the mirrors like this and onto a central tower. So, you have sun's rays reflected onto this. Now, the advantage of this type of smaller reflectors, as we have shown in the case of heliostats or this Fresnel reflector, each one of them can be tilted depending upon the sun's position. So, this is the receiver, not to get confused with the sun. So, you need some sort of a orientation or tracking of smaller pieces of reflectors than one large piece. And let me ask a question. Can you give me any device where there is a Fresnel refractor? Your OHP, overhead projector, has a Fresnel refractor. If you look through the top of the overhead projector, you will find something like your high school experiment of Newton's rings. That is a Fresnel lens. That is with a die, minutely varying angles of grooves that will make the focus and then reflect the object or the paper that you place on the overhead projector. So, if I have something like a parabola, so in a two-dimensional view, something like this will be my tube. So, I might call this a linear system. In other words, in the limit, the reflected rays will fall on a line, though that width of the line is finite for different reasons. So, parabolic reflector comes into the first category and the paraboloidal in the second category. This in principle is a point, though that point is finite, being sun casting a finite disk size, and you can't have anything smaller than a particular size by virtue of the sun subtending an angle of 27 minutes at the earth surface. Now, so far so good, but then I have to see that the rays are parallel to the reflector axis. So, this requires continuous tracking. That means, my collector, as the sun goes from east to west, my collector should turn from here. Okay, it does not move, but just to emphasize, this is here and this is here, normal the aperture plane. Okay. So, this has to turn from east to the west, whatever may be the angle, that we do not know still. So, this requires tracking, otherwise it does not work. So, you may have a fixed receiver and a moving aperture, that means the reflector. Or you may have a moving reflector, moving receiver, sorry, I am writing only on the other side, and a fixed reflector. And there is one more configuration one can think of, so that one does not come in the way of reflected sun's rays. Let us say it is a paraboloidal, and this is a mirror, this is also a mirror. They will be reflected onto this mirror, and it will come over here. Then you may have a pot, maybe a tea kettle. Okay. So that when you are handling this, you are not in the path of the sun's rays. Otherwise, you look here, it could be quite serious. So, ideally, if I want to follow the sun's rays all the time, my reflector has to have a 2 axis tracking from east to west and keep rotating up and down, because the sun goes from east to west along an arc, and that arc angle depends upon the season, right. So, if you have a surface, you will be going from, let us say, east to west. In that process, it may be also swiveling, in order that the sun's arc will be in the plane normal to the aperture. So, now we will consider different tracking modes. So, mode 1, the collector, or we shall in future refer it as the plane, which essentially means the aperture plane, because whether it is a parabola or paraboloid, whatever is the radiation passing through the aperture plane will reach the reflector, thereby getting reflected, or the refracted to be refracted. So, the collector or the aperture plane rotated about east west axis with one daily adjustment. Such that the sun's rays are normal to the aperture at solar noon. So, this is only one adjustment per day, simplest. Though we will see whether that is sufficient or not, for what kind of concentrating collectors this will do the job. So, if you want me to demonstrate it, let us say this is the aperture plane, there is a parabola behind it, or to my left is the east and to my right is the west. So, I make one simple adjustment per day, that means the slope beta is chosen such that sun's rays are normal to the plane at solar noon. If for example, in December when the sun's rays will be pretty low, I will have a higher slope, and in summer it will be steep sun. So, I may have a lower slope. Okay. So, it becomes nearing the horizontal and nearly vertical in winter, depending upon of course, the latitude. So, the idea is this is the aperture plane, to my left is the east, to my right is the west, and then I will tilt it like this, change the slope of this plane such that the sun's rays are normal to the plane at a solar noon, something like this. So, if you take for this arrangement, gamma is 0 because it is a east west axis. So, it is south facing. So, my gamma is equal to 0. Consequently, cos theta expression is simple, is cos phi minus beta cos delta cos omega plus sin phi minus beta sin delta. At omega is equal to 0, theta is equal to 0, right. The sun's rays being normal to the plane means 0 angle between the outer normal to the plane and the sun's rays. This means this should be equal to cos phi minus beta cos delta, and cos omega is at omega equal to 0 is 1 plus sin phi minus beta sin delta. So, this is satisfied if phi minus beta is equal to delta, right. Then this becomes cos squared delta sin squared delta. Cos squared delta plus sin squared delta is always equal to unity. So, I choose phi minus beta is equal to delta or beta is equal to phi minus delta every day. That satisfies my tracking mode. The sun's rays are normal to the aperture at the noon time, providing the minimum angle at the noon time. Consequently, during the rest of the time, for a south facing fixed surface for the day will be having a minimum of angle of incidence. So, my cos theta is now cos squared delta cos omega plus sin squared delta. So, tracking mode 1 and beta is phi minus delta, because if you look at the top equation, it does not contain phi, it does not contain beta. So, in that sense you will not have complete information what you should do about the tracking mode, but this is basically to tell that the aperture plane should be having a slope given by phi minus delta, then cos theta is given by this expression. And you have got a tracking mode 2 . We will do one step better than what we have done. Again, a east west horizontal axis, instead of one single adjustment per day, continuously adjust such that theta is minimum for all omega. So, it is a east west horizontal axis surface rotated about the east west axis such that the angle of incidence is minimum. In the previous case, the angle of incidence was a minimum and equal to your 0 when at noon time, which is satisfied by phi minus delta is equal to 1. So, that is what is written here. A plane is rotated about a horizontal east west axis with continuous adjustment to minimize the angle of incidence. Since the aperture plane is facing south, again gamma is 0. My cos theta is given by the same expression, cos phi minus beta cos delta cos omega plus sin phi minus beta sin delta. Now, our objective is to make theta minimum. So, what we do is we do d by d beta of cos theta and equate it to 0. That will give me the condition phi minus beta is given by tan inverse tan delta by cos omega. So, this is B or the tracking mode 2. Now, let us see if omega equal to 0, this means phi minus beta equal to tan inverse tan delta equal to delta, same as A. So, tracking mode 1 condition that the angle of incidence is a minimum at solar noon needs to be satisfied, and it did if phi minus beta is tan inverse tan delta by cos omega at omega is equal to 0, and at any other time I have to choose my phi minus beta according to tan inverse of tan delta upon cos omega. So, if you substitute in that, now I will get my expression for cos theta as 1 minus cos squared delta sin squared omega whole to the power 1/2, right. So, again we have to mention phi minus beta is tan inverse of tan delta by cos omega. So, you adjust beta with the time of the day as given by this expression, and then you will have the angle of incidence being minimum for this mode of tracking, where an aperture plane with a horizontal east west axis is rotated about the east west axis such that beta is minimum. In other words, it swivels around the east-west axis such that beta is adjusted with this equation and your theta is a minimum. Theta will be 0 only at noon time, but theta will not be 0 at other times for this mode of tracking. This is also a single axis tracking mode. So, we come to the third tracking mode, which is a horizontal north south axis with continuous adjustment to minimize the angle of incidence. This requires a little bit of explanation. This is my aperture plane. To my front is the south, let us say, to my back is the north, and this is east, and this is west. To my right is west, to my left is east. So, if I face the aperture towards east and keep on rotating it about the north south axis, which is horizontal, I will go from east to west, and at each instance I am changing the slope of the surface by certain amount as given by the whatever expression we are going to get. So, previously we had a east west axis, now we have got a north south axis. So, this should be rotated from east to west as sun goes, rises in the east to sets in west. So, now you can see from the definition of the azimuthal angle, if you take the projection of the outer normal to the surface, it will be always minus 90, that means towards the east, okay, as long as the time is before solar noon. After solar noon, it will be towards west. So, my azimuthal angle will be plus 90. So, this as it is rotating, whether it is beta is 90 degrees or 80 degrees or 0 degrees, or again in the other direction 10, 20, 90. My outer normal from this direction projected onto the horizontal plane will be towards east. Consequently, you have a gamma minus 90. So, you have only two situations, gamma equal to minus 90 for omega less than 0 and gamma is equal to plus 90 for omega greater than 0. So, the general equation for cos theta, if I choose to examine for let us say gamma equal to minus 90 cos theta, we have our general equation cos theta is equal to a cos omega plus b sin a plus b cos omega plus c sin omega, and in that a, b, c are defined in terms of phi, beta, delta and gamma, and you put them and write it down with gamma is equal to minus 90, you will have a simpler expression sin phi sin delta plus cos phi cos delta cos omega times cos beta minus cos delta sin omega sin beta. So, the third mode of tracking is around a horizontal north south axis, the aperture plane being rotated from east to west, and we realized that the azimuthal angle is either minus 90 for forenoon and plus 90 for afternoon, and the general equation for the angle of incidence will be in terms of phi delta and omega of course and the beta. Now, our job